Hi everyone, today in the B3 notes, we're going to be looking at systems of equations and inequalities. Recall that a system of equations is a set of two or more equations. A solution to a system is the ordered pair that is a solution to each equation. So a solution to a system is the point where the two lines intersect. Looking at these examples, you can remind yourself that parallel lines have no solution. And this fits the definition because they would never intersect. Lines that intersect once, we give that point of intersection as the solution. So for example, here these two lines cross at the point -4, 3, and here these two lines cross at the point 4, 0. So a solution to a system is the point where the lines cross. Down here in the next example, we're asked to create a system of equations that models each scenario. So you don't need to solve it, you just need to come up with the equations. It can be helpful to pick variables that match the first letter of the word of what they represent, but sometimes you'll see problems where they just use X and Y, and that's the same thing. Here I'll use letters that match. Adult meals are $6, children's meals are $4, and a total of $1,128 is raised. When creating the second equation, you have adults attending the event, you have children attending the event, and altogether there's 212 people attending the event. This is the answer to the question because you're asked to just come up with this system. In the next problem, the coin bank has dimes and quarters. So there are dimes and there are quarters. There are a total of 250 physical coins. In the next equation, you need to introduce the value of those coins. Dimes are worth 10 cents. Quarters are worth 25 cents, and altogether the value of the coins is $39.25. And so again, you're just creating the system. You're not actually going through and solving it. There are three different ways that we can solve systems of equations. The first one is by graphing. So when I solve a system by graphing, I'm trying to graph the two lines and find the point where they cross. On this one, the first line is ready to graph. So my y-intercept is at +1, and then my slope is down 1 and 1 to the right. And so here's the equation of that first line. My second line isn't ready to graph yet. I'm going to put it in slope-intercept form to graph it. So I'll minus the x from both sides, and then I'll divide both sides by -3. I'll get y is equal to +1/3 x minus 3. And now the second equation is ready to graph. When I graph my second equation, I'll start at -3, and then my slope is up 1 and 3 to the right, and that's all I need to find the point where the two lines cross. It's okay if you want to put the rest of the points on your graph that fit, but in terms of answering the question, it's not necessary because you found the point where the two lines cross. The solution to this system is the point 3, -2 because that's the point where the two lines cross when you graph them. In the next example, we're asked to solve the system by substitution. Notice that in the first equation, the y is isolated. So we're going to take the 3x minus 4, which is equal to y, and we're going to substitute it in for y in the second equation. So I'm taking out the y and I'm plugging in the 3x minus 4 for the y. That's the substitution step. Now I'll solve the resulting equation. So I'll start with the distributive property. I'll combine like terms. I'll add the 8 to both sides, and then I'll divide by 8. And so for this one, I'll get x equals 12. Once I know the value for x, I can substitute it back into either equation. Notice how it's easier to plug it into the first one. 3 times 12 gives me 36, and then 36 minus 4 gives me 32. And so using substitution, we determined that the solution to this equation, the solution to this system of equations is the point 12, 32. That would be the point where the two lines cross if you were to graph them. The third way that we can solve systems is by elimination. In elimination, you're looking to cross out opposites. Neither of these equations have opposites already created, so we're going to have to multiply to make them have opposites. In this first example, I can multiply just the first equation through by +2. Notice that when I distribute through a +2, the coefficients on the y terms will become opposites. So I multiply through by 2 on the first equation, the second equation stays the same, and then I add up the result. Opposites cancel, I divide both sides by 13, and I get x equals 4. To solve for the y value of the intersection point, I can plug x equals 4 into either original equation. Here I'm going to plug it into the first equation. 5 times 4 gives me 20, minus the 20 from both sides, and then I'll divide both sides by 2. So for this one, I'll get y is equal to -2. So the solution for this one, or the point where the two lines would cross if graphed, would be the point 4, -2. On the next example, none of them are opposites, and in order to make them be opposites, I'm going to have to multiply both equations through. Since the signs on the x's are already opposites, I'm going to choose to multiply through by +3 and +4. Notice that once I do the distributive property, the coefficients on the x's will be opposites, so they'll cancel. So I multiply each equation through, first one by 3, the second one by 4, and then I'm going to add up what's left over. The x's cancel, and then I'll divide both sides by 23, so I'll get y equals 3. Remember that next, to get the x value of the intersection point, you can plug y equals 3 in for y in either of the original equations. 5 times 3 gives me 15, minus the 15 from both sides, and then finish by dividing by 4. So here x equals 5, and so the intersection point in the second example would be 5, 3. It is very common that you would be asked to use systems to solve word problems. At an ice cream store, a family ordered 2 banana splits and 2 hot fudge sundaes and paid $18. Here I'm letting B stand for banana splits and H stand for hot fudge sundaes. The next customer ordered 5 banana splits and 2 hot fudge sundaes and paid $36. We need to figure out how much each one costs. Here I'll choose to use elimination. I can multiply through by a -1. That will make the coefficients on the h's cancel out. So multiplying through by a -1 changes my first equation to be this. My second equation stays the same, and then I'll add them together. The h's cancel out, and so I'll get b equals 6. So the cost of a banana split is $6. Next, I need to figure out how much a hot fudge sundae costs. So I'll plug b equals 6 in for b in either of the two original equations. I'm going to plug it into the first one. So 2 times 6 is 12. I'll subtract the 12 from both sides, and then I'll divide both sides by 2. So I'm going to get h is equal to 3. So the cost of a hot fudge sundae is $3. This question asks us, if the following customer has $51 to spend and buys 9 hot fudge sundaes, how many banana splits can that person buy? So what we're doing now is a different calculation. If banana splits cost $6 each, and if hot fudge sundaes cost $3 each, and they're buying 9 of them, we want to figure out how many banana splits X they could buy with a total of $51. So I'll times 3 times 9. I'll subtract the 27 from both sides, and then I'll finish by dividing both sides by 6. So I'll get X equals 4. So with $51 and buying 9 hot fudge sundaes, they would have enough money to buy 4 banana splits. In this example, Jane has nickels and quarters. Jane has a total of 36 coins. Nickels are worth 5 cents, and quarters are worth 25 cents, and altogether the coins total $3. You can put the decimals here if you want to. We're trying to figure out how many more nickels than quarters she has, so we'll need to figure out how many nickels, how many quarters, and then we'll subtract those two answers. Please note that you could solve this problem using substitution. I'm going to do it using elimination. So I'll multiply through the first equation by -0.5. My second equation will stay the same, and then I'll add up the two equations. In order to figure out how many more nickels than quarters she has, we need to figure out how many nickels she has. So I'll plug Q equals 6 back into either of the two original equations. Notice that it's a lot easier to plug it into the first one. And I'll minus the 6 from both sides. So she has 30 nickels in the bank. She has 6 quarters in the bank. How many more nickels than quarters does she have? Well, to answer that question, we'll take the number of nickels she has and we'll minus the number of quarters that she has. And so here we'll conclude that she has 24 more nickels than quarters. The next example is tricky, because although it could be represented by a system, the system would be nonlinear, and we haven't covered solving nonlinear systems algebraically in this course. The question says that the sum, so you're adding, of the digits of a 2-digit number is 10. So when you add up the first number and the second number in the number, you get 10. So that number could be 91, right? Because 9 plus 1 gives you 10. The number could be 82, because 8 plus 2 gives you 10. 73, 64, 55, or 46, or 37, 82, or 19. So those 9 numbers represent all 9 possibilities for which number could be the answer to the question. The next part of the question says when the numbers are reversed, the number is decreased by 36. So remember, decreased means subtraction. So when I flip the order of the numbers and I subtract the two numbers, 91 minus 19 gives me 72. And so that's not the answer to the question. The difference is supposed to be 36. So then I'll try the next one. 82 minus 28, but that gives me 54, which is not 36, so I know it can't be those. And when I do 73 minus 37, I get 36, which is what I was trying to get as my answer to the question. So I don't actually have to check the rest of the numbers because this would be the answer to the question. So make a note on your paper that here, we decided to use guess and check as our method of answering the question because in this particular example, it's pretty quick to find the answer to the question using guess and check. We're finding the original number, not the flipped number, and so your answer for this question would be the number 73. Here, we will solve this system algebraically. There's two numbers that they're talking about, so we'll let those two numbers be x and y. 2 times a number plus 10 times the second number is 20, so there's my first equation. 30 times the second number plus 3 times the first number is equal to 45. So I start by creating my two equations. Notice that on the second equation, the terms for x and for y are backwards, so you might want to flip these two around before you do your elimination. A lot of students think that elimination is easier when the like terms are stacked on top of each other like that. We need to figure out both of the numbers, so it doesn't matter which number you eliminate first. I'll multiply the first equation through by -3 because notice when I do that distributive property, the coefficients on my y terms will be opposites. So I multiply through by -3 on the first equation, the second equation stays the same, and then I add up the two equations. So I cross off my opposites, and then I divide both sides by -3. And so I get x equals +5. So one of the numbers, the first number, is +5. The next thing I need to do is I need to figure out what the second number is, Remember, to figure out the second number, you can plug x equals 5 into either of the two original equations. I'll plug it into the first equation. So 10 plus 10y is equal to 20, and then I'll minus the 10 from both sides, and I'll divide both sides by 10, and so I'll get y equals 1. So the two numbers are the number 5 and the number 1. However, the question asked what is the difference between those two numbers, and so the difference between them is 5 minus 1, and so we would get the answer for this question is 4. All right, so in the next example, we're looking at finding function value difference. The definition says the difference of two function values equals 0 at the x coordinate of their intersection point. So looking at these two examples here, linear functions f of x and g of x are shown. Identify the solution to the equation f of x minus g of x is equal to 0. We're trying to figure out when the difference between these two functions is 0. The difference being 0 means the lines are no longer different from one another, so they don't have distance between them, and that occurs at their intersection point. But you want to be careful with how you answer the question, because the time at which these function values is equal to 0 is equal to the x coordinate of their intersection point. So for A, we would say that f of x minus g of x equals 0 at the point x equals positive 4. So when x equals 4, there's no difference between these functions. They have the same output. They would both give you a 3. Similarly on B, the function values for these two functions are equal to each other when x equals positive 2. For both of these two functions, the output for x equals 2, the graph would give you negative 1. So you're not trying to figure out when the functions themselves are equal to 0. You're not trying to solve for intercepts. You're trying to figure out when the lines are giving you the same output. So when the lines intersect or when they're not different from one another. All right, this next example reminds you that the solution to a system is the point or point where the lines cross. In this example, you have a line and you have a curve. This is an example of a nonlinear system where there's just one line and then the other equation, in this case, it's a parabola. You're asked to state the solution to the system, if any. In the first example, the parabola and the line never cross. So here we would say that they have no solution. The line and the parabola cross once. They cross at the point 2, negative 3. And in the third picture, the line and the parabola cross twice. However, those points are not occurring at integer values. And so we can say in the box that it has two solutions. However, they are unable to be determined graphically. Here on this next example, it gives us a system of nonlinear equations that's graphed below. It says, which of the following are solutions to the system? So remember, solutions to the system are the points where they cross. So it looks like we have one here and we have one here. So this one has two solutions. 8, 9 is one of the points and 2, 3 is the other point. So the answer for this question, we would select C because of the numbered choices. 1 and 3 are the two ordered pairs that are solutions to the equations. The next example has us practicing graphing systems of linear inequalities. And so here there's two lines that are graphed. The shaded region is the part that's darkest shaded. And so in this problem, the solution to the system would be any points that are over here in the part that I've overlaid in red. 0, 0 is a yes. That would be an answer to the question because it's in the shaded part. 2, 3 would be a no. Although that point is on the line for one of the equations, it's not in the shaded part of the graph, so it's not part of the solution set. Negative 4, positive 4 would be a yes because it's in the shaded part of the graph. And then lastly, negative 2, negative 5 would be a yes. It's on the boundary line, but it's on a solid boundary line. And so it is included in the solution set, even though it's right on the edge. Here in this next example, we are going to solve the system of inequalities by graphing. So we're going to graph both lines. The second line is ready to graph. And so I can start by graphing that one. So y is less than 3 would be a horizontal line through the point y equals 3. It would be a dashed line, and then it's less than 3, so it would be shaded down. I'm just going to make two little arrows here reminding me that I'll shade down. I'm going to graph my second line first before I shade. The first inequality isn't ready to be graphed yet. I have to put it in slope-intercept form first. So I'll minus the x from both sides, and then I'll divide by 2. And so now this second line is ready to graph. My y-intercept is up at positive 4, and then my slope is down 1 over 2. This one's greater than or equal to, so it's a solid line, and it's greater than, so I'll shade up. So you want to make sure that you shade the region of the graph that works for both lines. If I'm shading underneath the horizontal line, but if I'm shading above the solid line, the answer to the question is going to be this region over here, because that's the region of the graph that's both underneath the horizontal line and also above the solid line. The next example asks you a similar question, except the graphs are already graphed for you. Let's take a look at the answer choices on this one to see how they're different. So the lines are all in the same places. The shading is all happening in the same direction. The only thing that's different is that some of the lines are solid and some of the lines are dashed. So to answer this question, we're going to want to look at the direction of the inequality symbol. The first one is less than, so the first one should have a dashed line. The second one is greater than, so the second one should also have a dashed line. You should be shading below the line with the positive slope, but then above the line with the negative slope, and both of the lines should be dashed. And so that's how we decide that the answer for this question has to be C. C is the only graph out of the choices where both lines are dashed. Here in the next example, we're asked to graph the system of linear inequalities, but notice on this one, there's 3 lines that we need to graph. The first 2 are all ready to graph, so I'll start by graphing those. X is greater than or equal to 2 is a solid vertical line through the point where x equals 2, and then I'll shade greater than, so I'll be shading to the right of this line. My next line is y is greater than or equal to -3, so this one's going to be a solid horizontal line where y equals -3, and when it's time to shade on this one, it's greater than, so I'll be shading up from this line. The third line isn't ready to graph yet. I'm going to put it in slope-intercept form first. So I'll subtract the x from both sides, and now it's ready to graph. So I'll start up at +4, and then my slope is -1, so down 1 and 1 to the right. This one is a solid line, and it's less than or equal to, so I'll shade down from this line. So now we have to consider all 3 of the lines simultaneously. You're shading up from the horizontal line, you're shading to the right of the vertical line, and then you're shading underneath the diagonal line. So the answer to the question is the points that are inside this triangle. The first question asks you to describe the shape of the solution region. So it's a triangle. You might also note that it's a right triangle, and then in addition to that, the 2 legs are the same length. So this is so it's not just a triangle, it's an isosceles right triangle. And then the last question asks you to find the area of the solution region. So since it's bound on all sides, we can find its area. Remember that the area formula to find the area of a triangle, its area equals 1/2 base times height. And then in a right triangle, the base and the height are the legs. So the base is 5 units long when you count it on the picture, and the height is 5 units long when you count it on the picture. And half of 25 gives you 12 and a half. And so the area of the solution region on this graph would be 12 and a half square units.